Okay, so let's take a look at a photograph. So here, what we're looking at, we've got solid zinc metal, okay, being put into a beaker that contains copper 2 plus ions. Okay. So again, the solid metal here, that's zinc, and it's being put into a solution of copper 2 plus ions. Okay. And so what we should see is that after a certain period of time, the zinc metal inside that beaker becomes corroded. So what's really going on in this process? So here, if we take a look at the molecular level or the atomic level, you've got zinc metals, and this is what the zinc atoms, and these are the gray balls right here. And what's going on is that when you've got a copper 2 plus ion that comes or that hits the surface of the metal, the two valence electrons from the zinc metal is transferred to the copper 2 plus ion. So eventually what happens is that on the surface of the metal, the copper becomes deposited, and the zinc atoms that were on that surface are now in solution. So you start to see the corrosion is actually copper, elemental copper, that's now on the surface of the zinc metal. And if you notice that the solution is definitely cleared up and become more transparent. And that's because you're now taking all the copper ions and they're coming out of solution. They're being deposited onto the metal. So this kind of a redox reaction, if we were to write that equation, what we're looking at is that we've got zinc metal plus copper 2 plus ions that are aqueous becomes copper elemental and zinc 2 plus ions. Okay? So that's the process that we're looking at. Okay. Now, this is a spontaneous process that releases energy. And what is the disposition of this extra energy? It's heat. So you feel the beaker, you're going to feel that heat that's generated from this reaction. Now, that heat is essentially wasted. Okay? Because all it's doing is going off. That heat is just escaping into the surroundings. Now, if there was a way that we could harness that heat, though, that would be pretty cool. Like, think of it this way. If we were to harness, if we take a look at the energy that's being emitted from, like, Niagara Falls. If you've ever gone to Niagara Falls, it's pretty cool. You've got, on the Canadian side especially, you've got, and on the American side, you've got turbines that are turning constantly because of the rush of the water. Okay. So you've got turbines that are churning because of the water that's going past those turbines. Okay. So think of this as a water wheel. We're harnessing the water from a waterfall in a water wheel. Or a hydroelectric plant, whichever way you want to look at this. So, if that's the analogy of a waterfall, and how we can harness the energy from a waterfall to make electricity for us. What must we do here in order to harness that heat, that energy from that reaction? So what we've got to do is separate the reactions to harness the drive of electrons. So the next question is, how do we harness the energy that we get from that reaction? So what we can do is construct something called a galvanic cell. And so here's how it works. All right. You've got a beaker that contains copper 2 plus ions. Okay. And you've also got a copper cathode. Okay. So that's one beaker. You've got another beaker here that contains solid zinc, and that's your anode, and that's got a solution of zinc 2 plus ions. Okay, we've got a wire that's connecting the zinc anode to the copper cathode. And on top of this wire, in between the anode and the cathode, we've got a light bulb. So once we make a complete circuit, that light bulb is going to turn on and it's going to burn bright. Now, in order to complete the circuit, however, we've got to also incorporate a salt bridge that contains some sort of salt. So in this case, we're going to use sodium sulfate, not only because it's relatively inexpensive, but sulfate ions can be, we can make copper 2 sulfate, and that's what the solution is over here, but zinc 2 sulfate is also that solution as well. So basically what we're trying to do is separate the reactions. So in one beaker, you've got one reaction that you have copper 2 plus ions in solution plus 2 electrons yields copper solid. Okay. You've got another reaction going on where the solid zinc is now with the electrons breaking up to release 2 electrons and become copper 2 plus ions. Okay. And so we've got movement here between the electrons going from the anode to the cathode, but we've also got anions also moving around as well. Okay. So what's going on is that the electrons leave zinc and produce zinc 2 plus. Let me write that N a little bit better. Zinc 2 plus. Okay. The electrons go to copper and adds to copper 2 plus. In solution to make elemental copper and energy. All right. And so that's what's going on here. So the name of this cell is has a specific, wow, I cannot even say that word. It actually has a specific name. We call this the Daniell cell. Okay. And this is just a particular type of voltaic cell. So also another thing to note, voltaic is the old school term. The new term is a galvanic. Okay, so you keep in mind that the names voltaic and galvanic are used interchangeably. Okay, so let's give some more important details of the cell. So of the Daniell cell. So the electrons flow with energy to light, which lights up the light bulb. Okay. The salt bridge allows movement to balance the charge without mixing. The copper 2 plus color fades which means the concentration of copper 2 plus ions are going down. It's decreasing. And so those are that's the information that we can get from this particular cell, the Daniell cell. Now, if we're going to talk in more general terms of what's going on at a galvanic cell, let's be clear on some of the terminology. So for the anode is where oxidation occurs. And we're losing electrons. Here, the electrons are produced and donated. The anions migrate towards the anode. Since zinc 2 plus is there, and it has a negative sign. For the cathode, this is where reduction occurs. The electrons are consumed. The cations migrate towards the cathode. And it has a positive sign. Okay, so one more thing that we can do with the Daniell cell, we could write the anode half reaction. So at the anode, you've got zinc that's solid, and it's becoming zinc 2 plus and releasing 2 electrons. Again, this is the oxidation half reaction. At the cathode, again, this is where reduction is occurring. Copper 2 plus is aqueous, picks up the 2 electrons, and becomes solid copper. And so if we were to add up the 2 half reactions, that gives us the overall cell reaction, which is zinc solid plus copper 2 plus. Aqueous yields copper solid plus zinc 2 plus. Okay, so this is our way of trying to harness the energy from a redox reaction. This is it. Because we know that species are giving up electrons and species are taking in electrons, we can actually use that energy, the electrons flowing from one source to another. We can divert the flow of electrons, go through a wire, and that's what we use for our electricity. Okay, so when it comes to electrochemistry, we can write these half reactions. We can write the full reaction. That's all well and good. We do have some notation, though, that we use for a galvanic cell. And so drawing pictures of cells is useful. It can get really tedious. Writing out these half reactions can also get somewhat tedious as well. So we have a shorthand notation to help us with that. So the shorthand notation goes like this. We're going to start with zinc solid, okay? And what I'm going to do is make a boundary, because remember that was your anode. You're going to have zinc 2 plus in solution. And remember, this is your anode. Okay? You have that beaker is connected by a salt bridge, which is your double line here. Okay? Connected to your cathode. So here you've got copper 2 plus, which is aqueous, and you've got a boundary between that and solid copper. So again, the right-hand side, cathode. So we make sure that the electrons are flowing from left to right. And so that's how we write this. So zinc has to go to zinc 2 plus to give up the electrons. Copper 2 plus takes in those electrons to become copper solid. Okay. So which way do the electrons flow in the cell? According to this notation, it's flowing from left to right. All right, so let's take a look at another example. Here you've got, let's take a look at the left-hand side. You got solid iron becoming Fe2 plus. And then on the right-hand side, you've got Fe3 plus and Fe2 plus. So you got a mixture of those two. And then you've got solid platinum. Okay, so there is no vertical line between Fe3 plus and Fe2 plus. So let me circle that. So why is there no vertical line? And that's because they're in the same phase. They're both aqueous. Okay. Now, why is platinum used in this cell? Platinum is non-reactive. So even though you have that mixture of Fe3 plus and Fe2 plus in that beaker, and platinum is your cathode, that platinum's non-reactive. It's not really doing anything. Okay. Now, which electrode is the cathode? It's the platinum. All right. And so that's how we write shorthand notations for a galvanic or voltaic cell.